5. Take a look at 5.2. We have our mid-segment drawn here. So that mid-segment, as a reminder, two things you need to know. DE is going to be parallel to AC. And more importantly right now, DE is going to be 1/2 of AC. So as a reminder, what that means is we can either, if DE is 5, AC is going to be 10. So we can do one of two things. We can take the mid-segment and we can multiply it by 2 to get the third side, or we can take the third side and we divide by 2 to get back to the mid-segment. So we have to be able to do it both ways. So we can do one of those two things here. DE is 1/2 of AC. So if we wanted to, we could double DE, and it would have to be equal to this 3x plus 25. So if I double 4x plus 5, we get 8x plus 10. And that will have to equal the 3x plus 25. Now, technically you could go the other way. It's just going to give you uglier numbers. If I wanted to divide it by 2, we're getting 1.5x plus 12.5. And that would have to be equal to our mid-segment, which was our 4x plus 5. So we can do it either way. We just want to keep the numbers nice. Right? So that's why we're going to solve this equation here on the right. So we subtract 3x from both sides, giving me 5x plus 10 equals 25. Subtract 10 from both sides, gives us 5x to equal 15. And we divide by 5, giving us x to equal 3. If you notice when we plug that in, 4 times 3 is 12. 12 plus 5 is 17. So like the DE was 17. 3 times 3 is 9. 9 plus 25 gives us 34 for AC. Notice your mid-segment here is 1/2 as big as that third side. Now what we're going to do today is we're going to start adventuring into a couple different pieces inside your triangle. The first one we're going to look at is what's known as a perpendicular bisector. And a perpendicular bisector is exactly what it says. It is going to be perpendicular and it is going to bisect something. So it is a segment, a ray, a line, or a plane that is perpendicular to a segment at its midpoint. So remember, to be a perpendicular bisector, we must be perpendicular to something. So we have our right angle, and we must cut it in half. So if I have some segment here, to have a perpendicular bisector to it, it must go through the middle of that segment, and it has to be perpendicular to it. Now, whether it's a ray, as I have here, or a line segment, or a plane for that, whatever it is, it must be perpendicular to it there. That is what a perpendicular bisector is. Now, the term we're going to use is this idea of something being equidistant. Right? To be equidistant essentially just means the same distance. If you're standing in the middle of the classroom, you are equidistant from the front wall and the back wall. Right? That's what the idea equidistant is going to mean. A point that is the same distance away from each figure. So this point P here, it is the same distance away from A as it is from B. If this thing on the left was 4 inches, this segment on the right would be 4 inches. That's what that term equidistant means. We would say that that point P is equidistant from the endpoints A and B. All right, taking a look at this perpendicular bisector theorem. What it's going to say is when we have a perpendicular bisector like we see here, what it is going to say is any point that is on it. So this point P was on it. I can take this point up here, we can call it Q. I can take this point up here, call it X. This point down here, call it Y. Any point that is on the perpendicular bisector will be the same distance away from each endpoint, meaning X to B will have to equal X to A. Or Q to A will have to equal Q to B. Any point that is on it, this point down here, Y. Y to A will have to equal Y to B. Any point that is on it will be equidistant from those endpoints. In a plane, if a point is on your perpendicular bisector, so this point C here is on the perpendicular bisector, then it is equidistant from the endpoints of that segment. So C to A will be equal to C to B. Now, the other part that it's going to come up with here, it's going to talk about if I have this other point down here, call it point X. The converse to it is going to be true also. Meaning if X to A is 10 inches, and X to B is also 10 inches, then this point X is going to be on the perpendicular bisector. Right, so it's just going to be the converse to it. If a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of that segment. So this point D down here, since it is equidistant from A and B, then D would have to lie on the perpendicular bisector. Remember two things though you need to be on your perpendicular or to be a perpendicular bisector. You do have to have both pieces. It must be perpendicular and bisect that segment. Take a look at your first example then. It says AC is the perpendicular bisector of BD. So I know it's going to be perpendicular and that BC and DC will have to be equal. What my theorem then says is any point that is on it, such as this point A, will be equidistant from our endpoints, meaning A to B will have to equal A to D. So this 7x minus 6 must equal 4x. To solve our equation, we subtract 7x from both sides. So negative 6 equals negative 3x. And then we divide. We get x to equal 2. Right? However, they want us here, instead of finding x, once again, remember, we've got to read the directions. They want us to find AD. So I need to take my 2 and plug it in. 4 times 2, AD will have to be 8. So there's our answer there. Let's take a look at our next example. It says, in your diagram, KN is the perpendicular bisector of JL. A says, what segment lengths are equal? Well, when I look at the picture, the easy one, we know JM and ML are equal. Right? Because both are 13. If KN is the perpendicular bisector, I see the perpendicular markings there, but it also means that that segment is getting bisected. So JN is equal to LN. And then finally, using my theorem, any point on that perpendicular bisector, so any point on here, such as K, has to be equidistant to the endpoints. So K to J and K to L will have to be equal also. So there are my equal segments. And then B wants to know, is M on that perpendicular bisector? If M is equidistant from those two sides, since they're both 13, yes, it will. If they ask why, my reasoning is because MJ is equal to ML, both at 13. If a point is equidistant from the endpoints, it is on your perpendicular bisector. Right? What you're going to see in this section and then the next two is going to be this idea that we're going to talk about some type of piece. Here we're talking about perpendicular bisectors. We'll do angle bisectors, segment bisectors. We'll do altitudes later. Each time we'll talk about what it is, and then afterwards we're going to talk about a certain property it will have in our triangle. When we talk about that property it'll have in our triangle, it'll be because they are concurrent. What this term concurrent is going to mean is that when three or more lines, rays, segments, intersect at the same point. So if I had this line, for three or more lines to be concurrent means all three of them have to go through this same point right here. So lines A, B, and C are considered to be concurrent because they all go through the same point. That point they meet at will be known as the point of concurrency, the point of intersection for those lines. So when you have your concurrent lines, boy, that was a terrible line. They all go through that point. That point is known as your point of concurrency. Right? And that point of concurrency is always going to have a property to it. So when we look at our triangles. So if I draw in three perpendicular bisectors here. So if I bisect this bottom segment, perpendicular, and I bisected it. Bisect this side, perpendicular to it. If I bisect this side, I will be perpendicular to it. Notice these three perpendicular bisectors, they all meet at a point. That point is going to have a property. Right? And that's what we're going to look at today. The property we're going to go over, we are coming from the sides. So my property is going to be that from the point to all three of my angles will be the same length. If this is 10 inches, this would be 10 inches, and this one would be 10 inches. So my point of concurrency is going to be equidistant from my angles here. Meaning, if P is that point of concurrency, P to A, P to B, and P to C are going to be equal. And that's what my theorem is going to say. The perpendicular bisectors of a triangle intersect at a point that is equidistant from the vertices of that triangle. In other words, if P to D P to D is a perpendicular bisector. P to E is a perpendicular bisector. And P to F is a perpendicular bisector. All of your perpendicular bisectors meet at a point. They meet at this point P. That point P is equidistant from your angles. So P to A, 5 inches. P to B would be 5 inches. And P to C will also be 5 inches. Right? And that's our theorem today. That's that property that we need to know. Now look at example 3. Right? Example 3 is essentially how we work on figuring out where to put cell phone towers and things like that. So you are trying to get the same distance away from 3 objects. This is the idea that's there. It says 3 friends are playing catch. You want to position yourself so that you are the same distance away from those 3 friends. So here's those 3 friends, friend A, friend B, friend C. To find your location, where you are actually going to be is where the 3 perpendicular bisectors all intersect. So there's 1. There's 2. And there's 3. This point right here is where you would want to be, where those 3 perpendicular bisectors all intersect. The last thing you need to know is that that point has a name. That point, it is known as a circumcenter. The point of concurrency of the 3 perpendicular bisectors. So 1 perpendicular bisector, two perpendicular bisectors. Now, if I draw my third one in here, remember, a perpendicular bisector is actually a line. So even though I would draw it coming this way, it's a line, so it would extend this way also. From this point to here, and to here would all be the same. And then there's your homework tonight.